Welcome to my presentation. Here I'm going to present volumetric 3D tracking by detection. This is a joint work for all the authors here from Technical University Munich and Area Grenoble. So this paper addressed the problem of 3D human shape tracking, which can be defined as follows. We observe a moving subject from multiple cameras, and we would like to recover the time-consistent dynamic model as shown on the right. It has several applications such as motion analysis and media content production. However, challenges remains to be tackled, such as large deformation between frames or long-term tracking. In the literature, there are two family approaches exist. The first one is volumetric EMICP, since it relies on previous results. So, as you can see, error tends to get accumulated, and there's no way to recover. Therefore, this kind of approach cannot handle large deformation properly. On the other hand, surface-based detection approach also exists. Detection means that the correspondence is predicted by some machine learning techniques such as random forest, and they are independent for each frame. So the behavior is similar to tracking by detection paradigm in 2D and avoids error from being accumulated. However, surface deformation models sometimes yield unrealistic deformation as shown in the red circle. And therefore, in this paper, we would like to present a fully volumetric tracking by detection framework that holds the merits of the two aforementioned families. It has the four following features. First of all, to yield realistic deformations, we apply volumetric deformation model that preserve volumes implicitly, and as you can see here, handle challenging poses better than surface-based tracking. Secondly, to avoid error from being accumulated, we would like the data association to be predicted frame-wise, frame-independently, as you can see here. And this is done by random forest, which requires some definition of features. To be invariant to pose changes and rigid body motions, our feature is based on distance fields. Last but not least, to include a variety of shape and motions, we devise a strategy to learn from multiple datasets, even if they are tracked with different shape templates. Okay, to be more specific, first of all, each 3D shape is represented by centroid overall tessellation, in short, CVT. A distance field can thereby be sampled at each CVT cell. And then each CVT cell is first described by our local feature, and then being mapped to the template domain by regression forest. Every cell gets a correspondence which is encoded in colors, and therefore our correspondence is volumetric, not surface-based, and this process is done for each frame independently. Now we show some visual comparison. Compared to the EMICP-based method, since our correspondence doesn't rely on previous frame, so it can handle large deformation and gets recovered from tracking errors more properly. And on the other hand, compared to the surface-based detection approach, it implicitly preserves volumes and yields more plausible deformation. And therefore, we always refer to our approach as volumetric tracking by detection because it holds the merits of the two. Please drop by our poster to have more discussions. Thank you.